Well, good evening, everybody. Okay, I know. Okay, it looks like Eric's away and Ken is away last minute, unfortunately. So I stepped in. So tonight chair. We have Charlie. Well, you both begin with a C. Uh, with VNA basics and intro to the NanoVNA. And we've been doing a lot of stuff with the NanoVNA of late too, so this will be timely. Or maybe it's a couple weeks too late. I borrowed Howard's NanoVNA to do some of the work, and then we'll have an quick update to our probe and backplane projects, and then we should have some time for some questions tonight. So I guess without further ado, Charlie, take it away if you're all set.
I am set. I just need to start sharing.
You should do something with a disclaimer, Peter.
Oh, okay.
I suppose. Yeah.
Okay. Well, long story short, we are recording our meetings and we make them available to the general public on our YouTube channel. So by participating in this meeting, we take it as you've agreed to those terms. Take it away, Charlie. I know I don't do it as well as Ken.
All right, let's see if I can get this going. Can folks see this chart?
Yes, we can.
All right, perfect. So I got myself into a bit of a rabbit hole probably over the last year, to be honest, around VNAs and what the heck are they? How do they work? What do we use them for? And I added on to that a practical example, which of course is the NanoVNA and an application that I did with it. Worth mentioning in this presentation is that a lot of the information that's in here I stole from Tektronix and a few other VNA vendors. So I want to give them a little bit of credit, at least, that I didn't do all of these charts originally on my own here.
Charlie?
Yes.
Could you hit the hide, hit the hide for the sharing screen, just in case you got something of importance at the bottom of your slide?
Is that gone?
I think so.
Okay, perfect.
And a better term than stole would be leveraged.
Certainly. Borrowed. All right. So let us begin. So when I started digging into this, I was wondering what exactly is a VNA. You know, and we all know the words, the vector network analyzer, but what exactly does that mean, and where did it come from? So the first VNAs were put together around 1950, believe it or not, long time ago, and they were defined as an instrument that measures the impedance parameters of an electrical network. So this could include purely resistive networks or complex impedance networks, active or passive components, and basically any impedances of any network that you can conceive of. The VNA can actually measure what those values are. Typically, they're expressed as the R plus JX rectangular coordinates for those of us who are used to the math portion of it. And they can also be expressed as a magnitude and an angle, which would be called polar coordinates, right? So if you look at the little picture in the bottom here, if you're going to express it as R plus JX, the R would be along the resistive axis, and the reactive part would be along the x-axis. In this particular case, it's inductive. So R plus JX would be defined by these 2 points where they cross the axes, or alternatively, it could be a magnitude of that vector, and then the angle theta is usually how it's referred to when you dig into this stuff. The example that we have here is a resistor and an inductor. There are two basic types of VNA measurements, whether they're transmission, where we take a stimulus signal, we drive it through some device under test, and we look at the output of it, or there are reflection measurements where we take that signal and we look at what is bounced back or reflected off the device under test. VNAs are typically a transmitter and a number of receivers that look at either the signal going completely through or that that reflected signal. So, you know, if the signal's going through a device, we can look at gain or loss, how the phase is impacted. Is there some electrical delay, and group delay? That is how the delay varies with frequency of whatever we're putting through that device. For looking at the reflection measurements, we're looking at things like return loss or standing wave ratio, or the impedance that, of whatever we're looking into. Worth noting that that these things are expressed as S21 or S12 measurements and S11 or S22 measurements. We'll talk a little bit about what those mean in just a second. So we'll talk about it now. Why not? So the S stands for scattering parameters, and the numbers that follow it. The first number is where we're measuring. That is, you know, whether we're actually looking at port 1 or port 2, and then the second number is the source of the signal. So, for instance, if we look at this one up here, our signal goes in port 1 and we're measuring it on port 2, that would be an S21 measurement. S being scattering parameters, what we're measuring across through here, and the first number being where we're looking at it, so port 2, the second number being where the signal is going in, which is port 1. VNAs, there are all kinds of professional models out there. Here are a couple of ones that you know, are used as commercial products. The satellite TV folks or the cable TV folks use this one on the top, for instance. It's got a bandwidth of 100 kilohertz to 1.5 gigahertz. It's a 75 ohm because cable TV tends to work in the 75 ohm domain. And it carries a sticker price of $25,655. A little bit of a cough there. The one on the bottom is a handheld portable unit. It goes up to 4 gigahertz. This one for the low price of $10,236. So these are not cheap devices. These bench devices, you know, are generally, unless you're extremely lucky, they tend to be beyond what the average amateur radio guy can afford. Enter the NanoVNA, a device that for the lowly sum of $66.51 at AliExpress here, can do 10 kilohertz to 1.5 gigahertz. And if if we go back up, what was that original $25,000 unit? Ooh, 100 kilohertz to 1.5 gigahertz. So, you know, not quite as much bandwidth as the NanoVNA for a couple of orders of magnitude less in terms of cost. So this device is one that that starts to get interesting for those of us in the ham radio hobby. The NanoVNA has a new version out for those of us who haven't poked at it. It's called the V2 for version 2. It has a little wider range. It'll go all the way up to 3 gigahertz from 1.5 of the basic NanoVNA, and a slightly larger display, for essentially double the money. And then top of the line of these little boxes that were invented a few years ago is one that goes all the way up to $300. That's the NanoVNA V2 plus 4. This is quite a capable machine. It goes up to 4 gigahertz, which can certainly be useful for some of the higher ham radio frequencies. But the cool thing about this version is that it doesn't actually use harmonics for measurements like the original VNA did. So this, significantly improves performance, way less trace noise, and better dynamic range, and a number of other things. So when I talk about trace noise and dynamic range and so on, what are the parameters that are important for VNA, particularly one of these little boxes that we're choosing? And so these key parameters are really about 4 key specifications that you need to look at when you're choosing a VNA. The first, and obviously the most important to consider, is the frequency range. It needs to obviously cover the range of frequencies that we're interested in for our circuit, whatever it may be. But also, in some cases, when you're looking at things like mixers and so on, you have to consider the harmonics. So having something that goes up to 10 megahertz might be just fine if you're doing measurements at say 7 megahertz at 40 meters. But in reality, if your circuit has any nonlinearity in it, and you're concerned about measuring what's going on at harmonics, well, you may need something that's not just 7 meg, but 14 for the second harmonic, or 21 for the third, and so on and so on. So choosing the frequency range is kind of important. You want something fairly large, but maybe you don't need to go between 3 and 4 gigahertz. Choose something for more money at 4 gig when something at 3 would do what you need. So of the key measurements, frequency range is the first. The second is dynamic range. This gets important particularly when you're measuring filters and things. If you want to put together a repeater, you probably want a dynamic range of this thing that goes down, close to 100 dB. 90, I think, would be sufficient, but bigger is better when you're trying to understand the depth of the notch of a filter. So consequently, the pricey VNAs, they offer a dynamic range up to maybe 120 dB. The NanoVNA V2 is about 90, and the V2 Pro version hits 96. The third parameter that you be worried about is trace noise. So when the trace is going across the screen, it will bounce around a little bit depending on noise in the system. And this is one of my pet peeves. Trace noise is typically measured in milli-dB, which is, in my mind, just a completely silly measurement. dB, has a very large range to begin with. So, 1 milli-dB is minus 30 dB. I mean, why you would attempt to create a new measurement value, I have absolutely no idea. However, at the end of the day, These devices typically will measure trace noise in milli-dB. Let's see what else. Is there anything else in this notice that's worth mentioning? Okay, I guess finally the last one is the measurement speed. How quickly will it, in fact, take these measurements? This becomes important if you're in a production environment where you're trying to measure a number of devices. Um, the amount of time on each device becomes important on what the throughput is. For us in amateur radio, it's less critical. Although, as I noted here, I'm not getting any younger, so we don't have to take too long to do a measurement. But at the end of the day, that's the fourth parameter that's important to consider. So just looking at some of the specs, just to kind of get our heads around what these things might look like. The original NanoVNA, 10 kilohertz to 1.5 gig. It had a dynamic range up to 300 megahertz of about 70 dB. Beyond that, 300 to 900 was 60 dB, and from 900 to 1.5 gig was about 40 dB. The frequency tolerance, 2.5 parts per million, and frequency stability, 0.5 parts per million. Had a grand total of 101 scan points. So when it, you needed to be careful when you were setting up the frequency range that you're sweeping, because there are only 101 points in there that you got. If you set up a range of 10 kilohertz to 1.5 gigahertz, you missed an awful lot of frequencies. If you set your measurement range down in the 1 meg to 2 meg, well, then you were getting a measurement every 100 kilohertz or so, or 10 kilohertz or so. NanoVNA's come a ways over the years, and so the latest version, the V2 version, its bandwidth starts off a little higher at 50 kilohertz, but it winds its way up to 4.4 gig. It has a 90 dB dynamic range. The Pro version actually 96. Frequency resolution of 10 kilohertz. Frequency stability of 0.5 parts per million. It can do actually 1024 scan points, a significant improvement over that 101, although this is, you get the 1024 with external software, which effectively what it does is it does multiple measurements, slightly offsetting the frequency each time it sweeps, so that it collects all of those specific data points. The noise floor is significantly better on the V2. It's sort of 50 dB at 1.5 gig and 40 dB at 3 gig, and the sweep time bumps up quite a bit to 0.25 seconds. The two charts at the bottom here, the first is trace noise, and as you can see, the trace noise is almost unmeasurable. These two charts apply to the V2. It's if you look at half a dB on either side, you just can't tell of any noise to speak of in here at all. And the noise floor in a sweep is worst case in the sort of 96 dB range, but it's averaging around the down 110. So it's very, very quiet. The original NanoVNA, its noise floor was higher. I couldn't find anybody who admitted to what those values actually were, but it was considerably higher than the V2. All right, so let's talk about basic VNA operation. Any VNA that you buy, no matter what it is, it has a signal source, and typically It has a minimum of 2 ports, where you've got, the source can kind of drive a signal into the device under test. There are receivers that will look at what gets reflected back out of it. Or if it passes through the device under test, then there's a receiver that looks at how that signal's been modified. And that information gets fed into some kind of compute device of some sort. Could be a device on the actual VNA box, or it could be an external PC and display. Essentially what the VNA does is that it drives voltage and current into the device, and these receivers measure the voltage and the current and look at what sort of phase response happens between the two, and based on that information, understanding the voltage and the current of either what passes through a device or what gets reflected from it, you can determine what exactly the network looks like that's in that device under test. Typically, as we mentioned earlier around the S parameters, if there are 2 ports and we're driving a signal, signals can be driven into either port 1 or port 2. Generally speaking, we'll drive a signal in from port 1, for instance, into the device under test. The S11, that is, we send from port 1 and we receive at port 1. That signal will be, whatever we measure at B divided by whatever we sent at A, or the reflected over the incident, in other words, and that will be calculated as the value of energy that gets reflected. This, on the other side here, this condition of A2 equals 0, it really is just saying that port 2 isn't transmitting anything towards the device under test, because in a reverse measurement, you could transmit from port 2, look at what's reflected from port 2, and in which case you would not be transmitting anything into port 1. So this is the case where where A1 equals 0. So this is kind of the math behind it. It's really fairly simple, straightforward math. And once you've done these measurements, this is how you calculate the results for comparison. VNAs, by the way, it's worth noting, don't all have 2 ports. Some have many ports. So if you've got a 4-port VNA, for example, you'd have 16 S parameters, right? So you'd have the S11, S12, S13, S14, and then S21, S22, and so on up into S44. NanoVNA, 2 ports, and for the stuff we do, that's probably more than enough. I can't honestly think of an application where you would need more than 2, but if you can spend the money and get a VNA that will allow you to do those measurements. Sorts of measurements you can do with a VNA. This is just a little example of the front end of a radio, right? So we're not even looking at the receiver portion. The intermediate frequency stuff is just represented by a block here. We're just looking at the very front end. So you can use the VNA to take a look at the antenna, understand how efficient it is for getting the signal from the radio out to the air, how much the signal is getting to the antenna, how much is getting reflected back towards the radio, And other things you can look at. You can look at the isolation, for instance, of the duplexer at the front end of it. You can look at what kind of amplification are you getting from the power amplifier. How well is the signal being converted to the new frequency? Are we generating any harmonics or any other garbage that we don't want? We can measure filters and see just how well those unwanted signals are getting attenuated or knocked out of our receivers. So lots of different kinds of measurements you can actually accomplish with that VNA. Apart from looking at a frequency of interest and seeing how networks behave, VNAs allow you to do swept frequency measurements as well. And so if we're sweeping the frequency, we can have a look at things like filters, for example. So here's a notch filter, I guess is one way of calling it, or a bandpass filter. So the VNA will tell us, just how good things are in the stop band, whether it be the lower part or the upper part, what the pass band looks like. You'll note that the pass band of the filter we're talking about here is the 6 dB bandwidth. And that's because VNAs work with voltage and current. They do not work with power specifically. Power would have to be calculated outside of that. So the passband of a filter, if we're talking about power, that would be a 3 dB bandwidth. But because we're really talking about voltages or currents here, it's the 6 dB bandwidth for a forward transmission through a filter here. The VNA basically, once we've designed our filter, the VNA allows us to figure out, to measure how that filter is actually performing versus the design spec that we put together. When it comes to an antenna, here's a return loss measurement. So, if you look at how much signal is coming back into your transmitter, at frequencies below the antenna frequency, lots of the energy is coming back. If you have a frequency that's tuned to 500 megahertz and you said something at 1 megahertz, most of it's going to get reflected because the antenna is a really bad match for that. As the power gets transferred to the antenna, less and less of it gets reflected, so that at the resonant frequency of the antenna, you'll get a minimum reflection coming back into whether you're doing this with whether you're looking at the transmitter or whether you're using the VNA with a signal source and looking at the reflected power or the reflected power in this particular diagram. So you'll get the essentially a null at the resonant frequency of the antenna. By the way, feel free to stop and interrupt me if something comes up while I'm rambling on here. There was a question.
Dave would like to speak.
Sure, go ahead, Dave.
Yeah, Charlie, if you go back a couple of slides to where you were defining, the math for, this slide. Okay, is it possible, see the reverse?
Yes.
You're measuring, so that would be the output impedance, that reflected coefficient B2. If you do the math or whatever, that could lead you to derive the output impedance, correct?
Yes.
Okay, is it possible to take, because the NanoVNA can't do an S22 measurement, but it could do a S11 and a S21. Could you not flip it around and put the goes in to the goes out of the DUT and measure what's get reflected back to determine the output impedance? I thought about doing that. I tried it and I never got good results. Is that something you could do, or is that something you shouldn't be doing with the VNA unless it's got an S22 port?
So if it's a passive device, let's say a filter, you can do that. It will be, you know, effectively symmetrical. You can flip it around and measure the other way around. If it's an active device, um, uh, generally speaking, you can, you know, you can't do a 2-2 measurement backwards through it anyway if it's an active device, right? Sorry,
So how would you?
a 2-1 rather. 2-2 you can do, but not a
So that
2-1.
the device, if it's because this is for an active device, so for an active device, you have to make sure the VNA can actually measure S222.
Correct. Yes.
Okay. Okay, fair enough. Thanks.
All right, I'll bop forward again here. One of the things I wanted to point out that's really important is calibration. Those of us who have NanoVNAs and so on, it's very easy to grab the thing, you know, bring up the last calibration we did on it and start measuring. And if you're doing a measurement where the absolute values aren't really all that critical, you're just kind of rechecking an antenna or something, you can probably get away with that. But if you're trying to do a real lab type measurement, you absolutely have to calibrate every single time you power that puppy up. The reason is that, you know, and this chart shows that there are kind of 3 types of errors. There are systematic errors, that is, you know, the absolute level that's being sent by the transmit portion of it, and so on. Those get removed by calibration. You get some drift with temperature or just time. Those get removed with calibration. There are also random errors, which could be noise related or data hiccups. Those don't get removed by calibration. They remain in the result no matter what. But you know, probably, you know, if there are 3 categories, then at least 60% of your errors get removed just by doing a calibration before you attempt to take a measurement. So, whether you've got an expensive commercial machine or a low-cost NanoVNA, calibrate every single time you go to do measurements, and every time you power up, every time you reconfigure for a different frequency range, take the time to do a calibration. It seems painful, but it's absolutely worth it. Looking at this a different way, there's a factory calibration that you know, covers up to the edge of the ports. And essentially ensures that those signals meet specs. Then the user calibration that we do before we take a measurement takes everything from those physical ports on outwards into effect. So cables, adapters, you know, you've unscrewed the SMA connector and screwed it back on again, and it's ever so subtly different. You need to redo the calibration to make sure that that gets included in the measurement and doesn't add to the error of the overall measurement. There are typically 4 different kinds of calibrations that can be done. You know, the super cheap and dirty one for things like even for the NanoVNA, you basically do an open or a short measurement to calibrate, and then go straight to your device under test. Same with a through measurement. You know, you do a quick zeroing effectively of a signal through a short effectively, and then the device under test gets stuck in. It's very simple, very quick to do it this way, but it is less accurate. The one that we typically do for the NanoVNA in particular is we do a test with an open, we do a test with a short, we do a test with a load, we do a test with a through signal from port 1 to port 2, and then we put our device under test in the circuit and do those measurements. So this is quite accurate. You know, the problem is there's quite a bunch of measurements to do here. It takes some time, but it's, for us, it's the right thing to do, is this 2-port 1 path approach. Yes.
I have the H4, and one of the things they talk about is the isolation calibration, and I've never really been clear what that's about.
That is basically this through measurement with nothing in here, just an open circuit between here.
Okay, thanks.
So the third type, if you've got a VNA which is capable of doing measurements, you know, the 1-1, the 1-2, the 2-1, the 2-2 type measurements, you would need to do those opens and shorts against each of the ports. This is not really applicable to the NanoVNA because it doesn't. It only has a single signal source. And then the fourth type is an electronic. So those fancy, expensive VNAs actually have an electronic calibration block that does this open, this short, the load, the through, and so on internally using relays or FETs to switch in the loads. So it does it, you know, very simple, very fast. You touch the button that says calibrate, it goes clickety click, and it's done calibrating, and then it can do your measurement. It's so very simple, very fast, very accurate, and tends to be quite pricey. It's one of those features that that you pay extra bucks for sure. Not available in a NanoVNA. The NanoVNA really, the 2-port 1 path calibration is the one that we should always be using. The other cool thing that VNAs can do, you know, most of the stuff we've talked about up to this point is in the frequency domain, but using inverse Fourier transforms, they can actually do stuff in the time domain. So some of the more recent VNAs, the V2, I'm not sure if the H4 can do this as well. It probably can, but I haven't been digging into it, mostly because I don't have one. But because you can do stuff in the time domain, you can do things like time domain reflectometry. So time domain reflectometry can do things like measure the length of a coax cable. If you've got a break in a cable somewhere, it can tell you exactly where that cable is. Essentially, the way it works is that it fires out a pulse and looks at energy that gets reflected from discontinuity, and essentially, if you know, speed of light signal goes out and gets reflected and comes back. the amount of time it takes for that to happen tells you the distance that's traveled, and there consequently you can figure out, where we've got discontinuities or a break in a cable, for example. So, in this particular graphic here, connectors will have a bit of a discontinuity, and you can see, here there's a bit of a reflection from the connectors, but this huge discontinuity is much larger than anything else that's coming back. So the VNA can essentially tell you where the break is in your cable. Pretty useful function, particularly businesses, the cable TV guys and so on find this sort of thing extremely useful when they get a cut in the cable. It's really hard to tell where it is, particularly if it's underground. Somebody's broken it with a shovel or something. Very, very, very useful piece of information. Great function. The other thing that you can do is swept power measurements with some VNAs. So what this does is essentially it starts out with a very small signal and cranks up the signal more and more and more and more. If your amplifier has a limit to how big a signal it can handle, well, that may be how far the signal can swing towards the rails, where your power rails are, and so on. Eventually, it's going to start getting nonlinear, and then it's going to just flatten out where you're stuck up against the rails on the amplifier, for instance. The specification is typically where you've got 1 dB of compression. That's considered the top end of your amplifier. And so VNAs can do this measurement as well by sweeping the power from low levels to fairly high levels. Coming back to our old buddy, the NanoVNA, one of the main complaints we get from folks is it's got this teeny tiny screen and I can't read it, and I stick it under a magnifying glass and it's still hard to read, and I touch buttons on it and the wrong thing happens because my finger is way fatter than the area where the touch screen is supposed to be. Lots of grumping about the screen size. The H4 with a 4-inch screen is a little better than the older 2.8-inch screen, but it's still teeny tiny. The good news is it fits in your pocket. The bad news is it's teeny tiny, hard to see and hard to use. So it didn't take very long for someone to come up with software which runs on, a laptop or a tablet or something of that nature that essentially gives you a much larger screen, and you can effectively put, type the parameters in on the keyboard. And rather than having to look at that small screen, you can get the results of whatever you're measuring displayed on something quite a bit bigger. This, by the way, is the results of an end-fed half-wave antenna, and I'll talk about it a bit more as we get a little deeper in the presentation here. Hello?
I have a question. Can you go back to the calibration? You can do calibration on the NanoVNA Saver software as well. I've read that you should do the calibration on the Nano itself and then do it on the Saver. That's one question. And the other question is the number of points. I gather you can divide the sweep range up into segments. At the top left is one segment in the box, at the top left in the sweep control box. If you use more than one segment, does that in effect mean you're using more points? Is that how you would go about increasing the number of points, calibration points?
Good question, and I'll be honest, I don't know. I have not experimented with that, but it does sound correct. As far as the calibration is concerned, I would not redo the calibration. If I'm doing the calibration on the actual device, I wouldn't attempt to redo it here. All this is it's a remote control. It's nothing more than that. It just the information that you put into the NanoVNA is the same stuff that you do on the screen. It's just a slightly different interface, and the display is the same stuff that would get displayed. It's just broken out into a few different charts rather than having them all on the same little screen.
Okay, yeah, thanks. The other thing is, when we did this for the probe design, and we used the NanoVNA to measure impedances, and one of the things that I noticed was that although you can set up the H4 to measure 400 points, this thing only allows 100, which I wondered about whether if you, I would have thought you'd be able to set up 400 points, but that's just another question I don't know the answer to. Okay, thanks.
Yeah, sorry, I don't know the answer to that one either. Go ahead.
Charlie, does the does the software cover off every function that's in the hardware itself?
I believe so. Now, I haven't made a career of going through everything that's going on. The things that I want to do are certainly in the NanoVNA Saver software.
Is there other software out there besides Saver, or?
There are a couple of other programs around. They're subtly different, but honestly, this one seems to be the one that everybody's using.
Okay. If you go and look at the groups IO for the Nano, there's a 2 or 3 of them in there, but I think this one's the best one. I haven't used the others, but I like this one.
Yeah, I agree. I've used it. Why change now?
Mm-hmm. Yeah.
So we can probably have a bit of a debate about which of these things are most useful, but for me the most useful part of these measurements and displays is the Smith chart, and the NanoVNA does an impedance Smith chart. That's this one, which is this is the commercial version of it, where the nominal impedance is here in the center. For the stuff we're doing, this would be 50 ohms. It's labeled as 1, so you normalize stuff. If I measure 50 ohms, I divide by 50 ohms and normalize it, and I get this 1 in the center of the chart. This side is infinity, this side is 0 ohms. The resistance tends to be across the middle of it. Things that are inductive are in the top half. Things that are capacitive are in the bottom half of the chart. And so you can, this is really just that R plus JX stuff we talked about early on in the presentation, but it's drawn with curves in the lines rather than a straight grid, and there are good reasons for that. Yes.
See if I word this correctly. When we were doing probe measurements, we found that really we discovered that the accuracy of impedance, I think, wanders once you start getting close to a K, or certainly above 500 ohms, that kind of thing. But just it made me think of this when you were saying on the right side of the Smith chart, you're at infinity, and the left side, you're at the short. So that means if we had 50 ohms in the dead center and you're at infinity to the far right, how accurate is it when it's halfway between? Like when you're up in 10K, 20K, and 1 meg and stuff like that.
Yeah, if you're way off the nominal impedance, it's the ratios can get a bit goofy. I mean, on this chart, 50 ohms would be here, 100 ohms would be here, right? So and 1,000 ohms is here, so you can see that you're the lines are getting pretty close together here to try and accurately measure this stuff.
Why. Now I can see why. Okay. Right.
So
Yeah.
okay, so I mentioned that this is an impedance Smith chart. There's also an admittance Smith chart, which looks exactly like a mirror image of this. And occasionally, you'll see impedance and admittance Smith charts overlaid on top of each other, looking something like this. Now, this looks like it's adding considerable more confusion to the chart, but it actually helps you quite a bit when you're doing impedance matching. And the reason for that is let's take this one as an example. So let's say I make a measurement, and my measurement is here where this dot is. If I want to try and get it, more resistive, series inductance will move it along this red line till I want to get it to, where purely resistive is in the center here. If I add series capacitance, I'll move this way on the line away from the center. Series resistance moves us in this direction. But the admittance stuff, when you're correcting impedances with it, would be components in parallel. So for instance, if I were to add inductance rather than in series, like I've done over here, if I added it in parallel across the load, it would move me along this curve, which would take me down pretty much bang on to that 50 ohm center that I'm trying to achieve, right? So, you know, for any circuit like this, there is a series equivalent and a parallel equivalent. So, using the reactance portion of it, you get the series equivalent. Using the admittance portion, you get the parallel equivalent, and it's great to do this on paper. The problem is that the NanoVNA does not give you these two charts. It basically only gives you this one, and with a lot fewer lines on it. So if you're trying to figure out corrections, you may actually need to take the values and drop them on a paper copy of this chart to figure out what you need to do to put, say, in parallel, for instance, in order to correct the impedance that you're looking for with a single component. So coming back to this NanoVNA Saver software chart, I wanted to do some kind of an example of what sorts of things you could do with the NanoVNA, and the example I chose is my end-fed half-wave antenna that I use for playing with HF. It's strung up on my roof right now. Mostly because I'm now living in a spot where I don't have a tower and there's lots of hydro lines around, and that's seems to be the best approach for getting something up in the air. So I cut the antenna when I do the measurements of it, and I did these measurements with the transformer in place. Lo and behold, I'm resonant I did my measurements at 20 meters. So I set my markers at 13 meg and at 14.1 meg, 14.1 being the frequency I wanted to operate at, basically. And lo and behold, this green marker sitting here on the line shows that I'm pretty much purely resistive at 14.1 megahertz. In fact, if I go and look at the values, I'm resistively speaking 17.6 ohms and 209 milliohms reactive, minus J209, so just ever so slightly capacitive, tiny amount. But when I look at things like the the standing wave ratio and the return loss, they kind of suck. And they kind of suck because although my antenna is resonant at the right frequency, um, I'm not anywhere near the 50 ohms here. I'm way out to lunch. If I look at these graphs here, for instance, of the impedance, I'm looking at in terms of reactance. The purple line is reactance here. I'm showing plus 857 milliohms, minus 857 milliohms. So I'm right in the middle. I'm just about perfect as far as reactance is concerned, but my resistance is very, very low. It's way down in the 17.7 range. If I take a look at what 17.6, I guess, if I look at what the marker is telling me. So what this tells me is, hey, you cut the wire the right length, but the impedance is wrong. You need to fix it somehow. So the reason for that, I believe, is that my feed point isn't actually right at the end of the half-wave antenna. If you look at a standard half-wave antenna, with its maximum voltages at the ends and maximum current in the middle, if I feed it right here in the center, that is the standard dipole, and it'll have a feed point impedance of, on the order of 73 ohms. If I get out to these ends, I'm about 2,500 or 3,000 ohms out at the ends of it, depending on how high I am above ground and so on. And as I slide my feed point along here, somewhere between 3,000 ohms and 73 ohms, depending on where that feed point is, that impedance will drop. So clearly, my feed point isn't actually at the end of the antenna, even though I'm connected at the end of the wire. And the reason for that is that, a portion of my coax, I've probably got, maybe call it 15, maybe 20 feet of coax before I go into an ugly balun, which blocks current flow on the outside of the coax. That's effectively becoming part of the antenna. So it's the equivalent of having slid this in a distance. And so the feed point impedance is lower than what I would want it to be. So if the VNA reads 17.6 ohms, we'll ignore the reactive portion for now because it's almost nothing. And my transformer is a 49-to-1 transformer. The actual impedance I'm seeing at the antenna is 862.4 ohms. That's very simple math. So if I need 862 ohms at the feed point, then the transformer ratio needs to change. It needs to be, the 862 divided by 50 to 1, or 17.25 to 1, which means a turns ratio of 4.15 to 1, call it 4 to 1. So if I rewind that transformer with 2 turns primary and 8 turns secondary, I should see 53.9 ohms at that point. The reactive portion is going to get transformed as well, but since it's almost perfect, don't need to worry about it too much. And consequently, at our frequency of interest, I should have a really perfect match here. So so that's what I did. And in fact, it worked. And I did this, I'm going to say about a year ago, 10 months ago. So when I started putting this presentation together, I realized I forgot to take a picture of the NanoVNA saver screen when I did it. So no problem. We can bang this together really quick, and I can do a screen capture and put it in the slideshow. What actually happened was when I opened up the transformer to do this, I figured out that First of all, it wasn't a 49-to-1. It wasn't a 7 turns to 1 turn ratio. This was a transformer I've been messing with, and so I basically had 15 turns to 2 turns, or 56-to-1 ratio, and so redo that calculation properly, and instead of 860 ohms, the antenna feed point impedance is really 990 ohms. So I went off and said, okay, well, now I need a slightly different ratio. And so I set off to make the transformer with that slightly different ratio. But so two turns primary and 9 turns secondary. But being the lazy kind of guy I am, and since this was mostly a science experiment rather than actually redoing everything on my antenna, it occurred to me that I could, in the middle of the transformer here, where the winding goes across, I could scrape some of the enamel off and connect there, and lo and behold, I'd have an 8 turns secondary. I just leave this end here open, unconnected, and connect my antenna to this midpoint here. So that's what I did. And then when I did the measurement a few days ago to take this picture to show you the wonderful results I got, I didn't get the wonderful results I'd hoped to get. Things had changed a little bit. If we take a look at the Smith chart here, you can see that the antenna seems to be more reactive rather than coming in here, bang on at 1 with no J component at all. Well, it now does have a bit of a J component. In fact, what I measure is 58.3 ohms resistive and 12.2 ohms rather than the milliohms I had before. When I look at the return loss isn't bad, but I'd much rather have it up here, even better. And the SWR is sitting at 1.24, which is what I kind of calculated it would be, but clearly if I look over here, it could be better. And this is the reactive component. So I'm going, well, what the heck happened? All I did was change the transformer. And then it occurred to me, well, wait a minute, this thing's looking more more inductive, which suggests the antenna is longer than it should be. Gee, if you take 64 feet of Canadian Tire speaker wire and string it up over the course of the winter with ice and things on it, it might get stretched a little bit. I suppose I could have bought the expensive antenna wire, which doesn't stretch as well, but I didn't. And so it's a few feet longer than it was before. So once all the foul weather is out of the way, I'm going to go up on the roof and cut a few feet off of it, and that should resolve this and get it back to the middle. But to be fair, the standing wave ratio has gone down to 1.3, which isn't bad. It was nearly 3 previously, so it's doing its job. And I probably would never have noticed this if I wasn't using the NanoVNA to do these measurements. That's what I have for charts. How are we doing? Any other questions? I see. Peter, I think you were first.
Yeah, I think Howard's up next. Yeah, where was it? Going way back to the first. First off, that was really informative and eye-opening in a couple of areas. So thank you for that, Charlie. At the very beginning, you talked about length of delay and electrical length delay and group delay. I didn't quite catch what the difference was between the two. Could you explain that again for me?
Yeah, so group delay is the difference between, so I've got an absolute delay, let's say at 1 megahertz. The delay might be different at 2 megahertz, 3 megahertz, and so on. So if I've group delay is the delta between those things across a given band of frequencies versus an absolute measurement at a single frequency. So for instance, if let's say I'm FM modulating a signal, the modulation will have different frequencies going across effectively in a group, if you think of it that way. And the delay will be different depending on which frequency you're at.
Okay, good. Thank you.
Who is next? Howard, I think.
Howard, I think you're up next.
Yeah, thanks. Interesting presentation, Charlie. Thanks. And timely, just by coincidence, when I was looking at full-size spectrum analyzers, there's a model that had a single port VNA built into it as well. But my question is it fair if the NanoVNA has a bandwidth, is 96 dB, and a real spectrum analyzer VNA has 90 dB, is it fair to compare that because of the difference in resolution that you get from one unit to the other? Like, will you see that difference in the cheap unit versus the real one?
So the typical NanoVNA that most of us own have about a 70 dB dynamic range. The latest and greatest V2 version, which I don't think any of us in this group own, that's where you get into the 90 dB, and then there's the V2 Pro, which gets up to 96. That the quality is actually meeting or exceeding what you get with the $2,500 unit. It absolutely is. And it fits in your pocket. Like, these are amazing little devices. They have other shortcomings, the level of signal they can put out, and noise, and well, just the tiny screen. But these are really getting to be quite comparable to a very expensive commercial machine.
Interesting. Because I was surprised to see that the dynamic range of the real one is slightly less than the nanos.
Yeah. But again, those are the V2 versions, which are a couple of $100. The
Right.
H4 version is in the kind of 70, 80
Right.
dB range. Yeah.
Right. Okay, thanks.
Any other questions for Charlie? Okay, well, thanks very much, Charlie. That was, like I say, very informative. And of late, I've been thinking about maybe picking up a NanoVNA myself, but we'll see. See which version. Okay. Moving on. I think, Howard, do you have a question for us tonight?
Yeah, but I mean, if there's nothing else.
Yeah, no, we do have an update, but I thought maybe let's approach your question that you've got for us tonight, and then we'll go on to the updates after that.
Well, just a quick question, being an RF newbie here. So, so to deal with harmonics, or to adjust the amplifier to minimize the higher order harmonics, do you do that with a signal and adjust gain, or do you do it with a signal and adjust bias, or both, or neither? Like, do you adjust the bias the normal way and then inject a signal, see how it affects the harmonics, or do you need a signal in order to adjust to see the harmonics change?
I think, I mean, I could be wrong, but I think you adjust the bias first without a signal.
Right.
That would be the idle current through the FET, and then And then once that's set according to the spec that it needs to be in the application, then you would I would inject a signal into the radio to confirm what it's doing on, and looking at the output, make sure you're not, overdriving it, right? But I think your idle current has to be set first without a signal, and then after that you go for checking harmonics and all that kind of good stuff. You would have to inject a signal source in there. Dave, you got a comment to that as well?
Yeah, Howard, when you're dealing with amplifiers, there is DC and there's AC. Okay, by you setting the bias, okay, that's a DC parameter.
Right.
Okay, so you're purely like all caps are open circuit, so which means there's no signal coming in.
Okay, that makes sense.
You're just dealing with DC, because what happens is that you're putting a current through the BJT or the MOSFET. You're putting a current through it, okay? And on that current, you're going to superimpose a small AC signal across that current. So you got this current coming down, right? Can you visualize that? You got a current coming down through your MOSFET, right? It's got a current, and that current, you're going to wiggle it a little bit with the AC, because, okay, you've got a voltage on it. Let's take a MOSFET, okay? So your MOSFET, let's just say you got 3 volts. I'm just picking a number.
Yeah.
Let's just say you put 3 volts on the gate of the MOSFET, and that's going to generate, say, 100 milliamps. I'm just picking numbers. Doesn't matter. Okay, it's going to generate 100 milliamps going through the MOSFET, right? So now that's your DC bias point. That's your DC bias point. Now, on top of that, you're going to superimpose on that 3 volts. You're going to superimpose an AC signal, maybe a 1 volt peak to peak. So it may go up to 3.5 volts, and it may go down to 2.5 volts. You're superimposing an AC voltage on that, and that's going to cause the current to wiggle on the output. And that wiggle on the output is bigger than the wiggle on the input, and that's your amplification. You understand that?
That makes sense with DC versus AC. So then if you're overdriving it AC wise, then that's the limiting factor if there's excessive harmonics then?
Yeah, so what happens, the way you get harmonics, distortion, okay, what that comes from, if you look at the characteristic of a MOSFET, okay, it's linear over a small region.
Right.
The MOSFET is only gonna, you put 3 volts in, you get 100 milliamps out. You put 3.1 volts in, you get 120 milliamps out. It's a linear relationship. It's a linear relationship between the voltage and the current. Now, that's only across a specific range. If you bias it close to the top of that range where the knees over, okay, what happens? It starts clipping, and that gives distortion. That gives harmonics.
Okay.
Same thing at the bottom. If you bias it too low, the bottom, you're gonna get that clipping. If it's biased exactly in the middle, and as you said, you put a signal that's really big, and it's going to take it up to the point where it bends over the knee, it's going to clip, and it's going to generate distortion. It's going to generate harmonics.
Okay.
Does that make sense?
That makes sense. I wasn't thinking of the differences between the DC and the AC, but that makes sense.
Michael, you got a comment?
Yeah, just going back to Charlie's presentation where he had the graph that showed the compression point. What Dave is saying is you're starting out somewhere down in the bottom of that curve. So you add a little bit of AC, a little bit of RF, you're not going to drive it far enough into the higher part of the curve where he's talking about the knee. That's what he's talking about, getting into that nonlinear region, and that's where you get the harmonics. I think that's right.
Yeah, I was thinking about that when I saw that slide. So, okay, well,
as long as you keep in the linear part, as long as you keep it so your AC signal is not pushing you into that nonlinear part of the curve, you're okay.
Right. See, I was forgetting about the DC versus AC components. So that makes sense. So, okay, thanks. That makes it clear.
Okay, good. Any other comments, questions? Okay.
Yeah, I just say all this is very good for learning, I think.
Oh,
Excellent.
yeah, there's nothing like taking on a project to learn for
Yeah,
sure.
and Charlie's presentation was pretty good as well. I thought, in terms of learning.
Well, it's timing too, because we're all into using the NanoVNAs at the moment. So now it becomes pertinent, and we're going with the practical along with now the theoretical per se.
I did a similar presentation to the Amateur Radio Club, and I'm gonna do it again, and I'm gonna shamelessly plagiarize from Charlie's diagrams. I think they're really much better than mine. And that time domain reflectometry, it seems to me that I did a test with the Nano with a piece of cable and just measured the distance to the open with the NanoVNA. There's a way to do that. I know there is.